Welcome to Arc Dev Labs. It's good to see you.
Have you ever been scrolling through your photo feed and just stopped and wondered, how does this actually work? How does an app juggle billions of photos from millions of people all at the same time without crashing? Well, today, that's exactly what we're going to figure out. We're going to pull back the curtain and design a huge photo sharing app right from scratch. So where do you even start with something that massive? You start with the big one, the billion-user question. This is the question that forces you to think differently. We're not talking about cool features yet. We're talking about building a foundation that's so rock solid it can handle pretty much anything the world throws at it. Okay, so before we dream up any crazy architecture, we have to do the most important thing: define the problem. What are we really building here? What does working actually mean? This first step is the blueprint for everything that comes next. If we get this wrong, the whole thing falls apart. First up, let's get the basics down on paper. What does the app need to do? Well, users have to be able to upload photos, see a newsfeed, and follow other people. Simple enough. That's the functional stuff. But then there's the how. The app has to be super fast and it can pretty much never go down. And finally, we got to think about scale. Now, for a photo app, you can bet that people will be looking at photos way more than they'll be uploading them. And that little detail, that high read to write ratio, that's a huge clue that's going to shape all of our decisions down the line. All right, with our requirements in hand, let's start sketching out the big picture. What are the main puzzle pieces we're going to need to make this whole system work? Let's draw up our first draft. So at a super high level, it's actually pretty simple. You've got your phone, that's the client. When you do something, it sends a request. That first hits a load balancer. Think of the load balancer as a really smart traffic cop, directing all the incoming cars to a whole fleet of web servers. These servers are the brains of the whole operation, and they talk to two different kinds of storage: a database for all the small stuff like usernames, captions, and comments, and then this giant warehouse called object storage for all the heavy files, the actual photos and videos themselves. Now we're getting to the really juicy part, the data. How we decide to store and manage all those photos and build the news feeds, that's what's going to make or break this app. This is where the really big, important decisions happen. And that brings us to one of the all-time classic questions in system design. For all that metadata, user info, photo details, who's following who, do we use a traditional structured SQL database? Or do we go with something more modern and flexible like a NoSQL database? The truth is, there's no single right answer here. It's all about using the right tool for the right job. For our user data, which is all neat and structured, a SQL database makes a ton of sense. But the newsfeed? That's a totally different animal. We're not doing complex math on it. We just need to grab a long list of photo IDs for a specific user, and we need to do it insanely fast. That's exactly what NoSQL databases are built for, that kind of speed and massive scale. And let's be absolutely crystal clear on this point. We never, and I mean ever, store the actual photo files inside our main database. That would be like trying to park a freight train in a one-car garage. It's slow, it's crazy expensive, and it would bring the whole system to its knees. Instead, we offload all that heavy data to a dedicated object storage system, something like Amazon S3, which is literally designed to store trillions of files. Okay, so this brings us to a really clever trade-off we can make. When you upload a new photo, does every single one of our billion users need to see it in the exact same millisecond? No, probably not. So we can embrace this idea called eventual consistency. It basically means we choose to prioritize being fast and always available, even if it means a brand new photo might take a couple of seconds to show up for everyone. For a social media feed, that's a perfectly acceptable trade. So we've got our data storage figured out, but that's only half the battle. How do we get a photo from our servers to someone's phone on the other side of the world in the blink of an eye? Because let's be real, in the app world, slow is the new broken. When we talk about speed, we're really juggling two different things: latency and throughput. Think of it like a highway. Latency is how long it takes for a single car to get from point A to point B. Throughput is how many cars can drive past point B every minute. Our goal is to get that one car there fast, that's low latency, while also making sure the highway can handle a massive traffic jam of millions of other cars, that's high throughput. So what's our secret weapon for making things fast? It's something called a content delivery network, or CDN. The easiest way to think about it is as a global network of mini servers that store copies of our most popular photos. So when a user in Tokyo requests a photo, they don't have to wait for it to come all the way from our main server in, say, the US. They just grab the copy that's already waiting for them on a server right there in Tokyo. It's a game changer for speed. And we'll use a specific kind called a pull CDN, which is super efficient. Here's how it works. The very first time someone in a region asks for a photo, the CDN reaches back to our main storage, pulls a copy, and saves it locally. From that moment on, anyone else in that region who wants that same photo gets it instantly from that local cache. It's this awesome self-optimizing system that automatically figures out what's popular and keeps it close to the people who want it. The CDN is great for the photos themselves, but what about the data that tells us which photos to show in the feed? For that, we use another layer of caching. We put a super fast in-memory cache like Redis right between our app servers and our database. It acts like a bodyguard. When a post goes viral and millions of people are trying to see it, instead of hammering our database, all those requests hit the cache, which can handle it without even breaking a sweat. It's our system's shock absorber. So our design is pretty smart, and it's fast. But can it handle a real crowd? How do we take this blueprint and make sure it can handle not just thousands, but hundreds of millions of users, all using the app at the exact same time? Remember that traffic cop, the load balancer? Well, at this scale, its job is absolutely critical. It's not just directing traffic anymore. It's also constantly checking on the health of all our web servers. If one server starts to get overwhelmed or has a problem, the load balancer instantly stops sending traffic to it and reroutes everyone to the healthy servers. It's the key to staying online no matter what. So when we need more power, how do we add it? We use a strategy called horizontal scaling. Instead of trying to build one single gigantic, ridiculously expensive super server, which is a huge risk because if it dies, the whole app dies, we just add more normal, cheaper servers to our fleet. It's like having a huge team of workers instead of one superstar. If one person calls in sick, the rest of the team can easily pick up the slack. It's cheaper and it's way more resilient. Okay, we've made a ton of decisions to get here, and that brings us to what is maybe the single most important rule in all of system design. You can't have it all. Every single decision you make is a trade-off. Every single one. This whole idea is perfectly captured by something called the CAP theorem. You can almost think of it as a law of physics for large-scale systems. It says you get to pick two out of these three guarantees. Consistency, meaning everyone sees the exact same data at the same time. Availability, meaning your app is always online and responsive. And partition tolerance, which means the system keeps working even if parts of it can't talk to each other. Now, in a huge distributed system, network problems are just a fact of life. Things will break. So we have to have partition tolerance, which means we're left with a big choice. Do we prioritize being perfectly consistent or always available? Well, for our photo app, think about it. Seeing a slightly older feed for a few seconds is no big deal. But seeing an error message, that's a disaster. Users hate that. So we make the conscious choice to prioritize availability. We choose to keep the service online, even if it means the data isn't perfectly up to the millisecond for everyone, everywhere, all the time. So there you have it, a design for a massive, fast, and resilient photo sharing app built on a whole series of smart, deliberate trade-offs. We chose to be available over being perfectly consistent. But that leads to one last question for you to think about. What kind of app can't make that same trade-off? What kind of system would you absolutely demand to be perfectly consistent, even if it meant it had to go offline sometimes rather than show you the wrong data? If you can answer that, then you're really starting to think like a system designer.